Okay, this video covers more examples of sequence convergence and divergence. Um, so I want to start talking about the theorem that I've got at the top of the screen. It says that if an is equal to f of n for large n, remember that n needs to be an integer for sequences. So an is equal to some function f of n for large integer values of n, and the limit as x approaches infinity of f of x equals some number L, then the limit of the sequence is also equal to that number L. Graphically, we can think of this as some function f of x, some continuous function f of x, converging to a number like this, and then the sequence would be dots along that because it's only defined at integer values. Well, if the function approaches some number, if that black line approaches that number, because all of the red dots have to be along that, then it would have to approach the same number as well. All right, we get to use that theorem when we're talking about a sequence like this. So if I have a sub n equals, say, the natural log of n over n squared, again, we're looking at sequences where the function types are different. So we have a power function here with a natural logarithm. If you look at that as n goes to infinity, that's in the form infinity over infinity. And in Calc 1, we would want to apply L'Hopital's rule. Technically, L'Hopital's rule only applies to continuous functions when you're talking about x being a real number rather than n being an integer. So what we do to get around using L'Hopital's rule directly on a sequence is we say, okay, let's consider this function f of x equals natural log of x over x squared. Okay, obviously, f of n is equal to an since the formulas are the same. So we're proving this first part of this theorem. Now we're going to look at the limit of the function. So we're going to say, okay, the limit as x approaches infinity of natural log x over x squared, that's in the form infinity over infinity. So L'Hopital's rule says we can take the derivative of the top and the derivative of the bottom, and the limits of those two expressions are the same. That then simplifies in this case to the limit as x goes to infinity of 1 over 2x squared. The limit of that is 0. So now the two conditions from this theorem are true. an is equal to f of n, and the limit as x approaches infinity of f of x is equal to L, where L is 0. So then that means, because of that theorem, the limit as n goes to infinity of an is equal to 0 as well. Okay, so I want you to try a problem like that. So problem 2 is going to be a sub n equals n squared over e to the 3n. So pause the video, try this problem, and check it with me in a few minutes. Okay, so again, this is a formula where it's in the form infinity over infinity. So we're going to say let f of x equal x squared over e to the 3x. Then obviously we know that a sub n is equal to f of n. We look at the limit as x approaches infinity of x squared over e to the 3x. That's infinity over infinity, which is an indeterminate form. We can apply L'Hopital's rule. So it's the limit as x goes to infinity of 2x over 3 e to the x. The derivative of x squared is 2x. The derivative of e to the 3x is e to the 3x times 3 because of the chain rule, which can then be simplified to 3e to the 3x. This is still infinity over infinity, so we can apply L'Hopital's rule again, and we get the limit as x goes to infinity of 2 over 9e to the 3x. That then approaches 0, so we know now that an approaches 0. Okay, so far what we have looked at for limits of sequences. We've talked about using dominant terms when you have power functions over power functions, or exponential functions over exponentials. Remember, power functions are when you have x to a power. Exponential functions are when you have a number to the x. Those problems were in the first video on sequence limits. In the second video in sequence limits, we talked about the squeeze theorem. We also talked about the absolute value of an. We know that if the absolute value goes to 0, the original sequence goes to 0. And then if a sequence is alternating, we can make other conclusions when the absolute value goes to something else. And now we've talked about using L'Hopital's rule. When necessary. On the homework, you'll see some combinations of these things. Some other problems that are worth definitely looking at and looking at the solutions. These definitely require practice. In the next video, we'll talk about sequences that are bounded and monotonic, how to show that, and how that relates to sequence convergence. All right, thanks for watching.